Hi there, welcome back for the second part of our nuclear unit. Today we're going to talk about radioactivity. There are some elements that are naturally radioactive and some that are artificially radioactive. And we're going to talk about a concept called half-life. So first off, most elements have some isotopes that occur naturally that are radioactive, but the percentage of radioactive isotopes or radioisotopes is so low that we don't consider that element radioactive. So an example of an element like that would be carbon up here, okay? Most carbon in the universe is carbon-12, which is, of course, carbon-12 with a 6 down here. So if you think of it as 6 protons and 6 neutrons. So the vast majority of carbon is this isotope, and it is stable. A very small amount of radioactive isotopes are mixed in, like carbon-13 or carbon-14, but they're a fairly small percentage, so in general we say that carbon is not radioactive. Other elements down here at the bottom of the periodic table are good examples, such as radon, our noble gas radon, have a very high percentage of radioisotopes, so we do consider that element in general to be radioactive. So even though there might be 1 or 2 isotopes of radon that are not stable, the vast majority are unstable, and therefore that element in general we say is radioactive. So you might notice that all these elements down here at the bottom of the periodic table have that radioactive symbol, not the first part of the not the lanthanides, but the bottom half of the rare earth elements and this bottom row down here. We'll talk about that in a minute, but basically everything beyond bismuth is radioactive naturally. Radioactive isotopes, again, can be artificially created from stable ones by something called neutron bombardment, which causes a disruption in that 1-to-1 neutron to proton ratio. So again, if you had carbon-12, which is 6 protons and 6 neutrons, if you add a neutron to it, which remember is 1, 0, that's going to turn it into carbon-13. So it's still carbon, it still has 6 protons, but we've disrupted that neutron to proton ratio. So we've turned it from non-radioactive to radioactive. So we can artificially create radioisotopes. It's worth noting that all elements beyond bismuth are naturally radioactive. So again, that's why all of them have that radioactive symbol down here. All of those and all of those. These tend to spontaneously undergo alpha decay and beta decay to bring them closer to that stable nucleus, that stable 1.5 to 1 neutron to proton ratio for large elements. And also, all elements heavier than uranium, number 92, are artificially created and are always radioactive. So these are called the trans-uranium elements. That means beyond uranium. So again, uranium is down there, number 92, I believe. Everything beyond that is artificially created. So like all of these and all of these are artificially created through things like alpha bombardment or neutron bombardment, and they're always radioactive. Again, they're formed by bombarding a heavy atom, so already uranium, bombarding it with neutrons or alpha particles. Scientists have created elements up to about 118 protons. That's a noble gas if you count it out on the periodic table. 118 would be right over here under radon. 118 would be over there. That's about as far as they've gotten, 118. And it's hard to know and confirm those big giant elements because they usually decay almost immediately, so it's very hard to get any built up mass of them and or any detectable mass. And it's hard to detect them before they go away, before they decay. Devices that are used to give those particles, like the neutrons or the alpha particles, so it could be a neutron or an alpha 4-2. The high speed they need to get into the targeted nucleus are called particle accelerators. One type is called the cyclotron, and they're big, giant machines. You can see in comparison to the size of these people, it's a big, giant machine. Also, you might have heard of like the Large Hadron Collider. These are just particle accelerators that produce these unstable nuclei or large atoms, and they also produce a lot of other things. All right, so we've talked about how some isotopes are not stable and they will decay. They decay in a certain way, and the pattern that they follow is called half-life. Okay, so they decay at a certain rate. Half-life is the amount of time that it takes for one half of a radioactive element to change from the parent element to the daughter element. So that's from the radioactive element to whatever it's producing. So an example, radium-226. Let's study this one. There's radium-226 is a radioactive isotope. So the half-life of radium-226 is 1600 years. So how much of a 10-gram sample will remain after 3 half-lives? So what that means, I'm going to draw a really not fancy diagram here. If you start with 10 grams of radium, and I'm going to draw an arrow that's just called 1600 years. If you wait that long, half of it is going to be left over. That's the definition of half-life. So 1600 years is one half-life, and how much would be left? Half of it. So 5 grams would be left over. So that's after one half-life. The second half-life is another 1600 years. So that amount of time for radium-226 doesn't change. Each half-life is still 1600 years. But now we're going from 5 to half of that. So now we get to 2.5 grams remaining. And again, we undergo 3 half-lives. That's what the problem says here, 3 half-lives. So we're going to wait yet another 1600 years, and half of that will remain, 1.25 grams. So your final mass after the 3 half-lives is 1.25 grams. To answer the second question, how many years will that be? This is easy. It's just multiplication. You think to yourself, well, I had 3 half-lives, and each half-life was 1600 years, so you just multiply 3 by 1600. If you can do that in your head, awesome. If you want to use a calculator, you can use a calculator. So just so I don't make any mistakes on my video here, I'm going to use my calculator. 3 times 1600, it's going to take 4,800 years for that to happen. So 4,800 years total. Okay, so that's how half-life works. You basically take your original sample and you divide it by 2 for however many half-lives you encounter. So we took 10 and divided it by 2 3 times. 10 divided by 2, divided by 2, divided by 2. And to figure out the total amount of time it takes, you will multiply the number of half-lives by the length of one half-life. So let's do another example. Oh, this is just a graph here to show you again that half-lives are consistent. So to go from 10 grams to half of that, which is 5, the amount of time it took here was, let's just kind of round it off to maybe like 26 years. Okay. Notice that the next half-life is from about 5 to 2.5, so 5 grams to 2.5 grams, that's the second half-life. But the amount of time was the same. It was still about 26 years. The next half-life from 1.5 to 1.25, again, is still 26 years. The next half-life is still 26 years. So the half-life amount of time does remain constant. So let's do another practice problem. This one deals only with uranium-238. It wants to know how much of a 6-gram sample will be left after exactly 4 half-lives. So I'm going to take my 6-gram sample, and I know if I'm undergoing 4 half-lives, I'm going to divide by 2 how many times? 4 times. So 6 divided by 2, 1, 2, 3, 4 times. So of course you could do divided by 2 to the 4th power if you want to, but I'm going to keep it simple here. So I'm going to divide by 2 4 times. So I'm going to switch over to my calculator, and I'm going to put in 6, and I'm going to divide by 2. Divide by 2, divide by 2, divide by 2. So I'm going to divide by 2 4 times, and we see that the final amount left over is 0.375 grams. And that's consistent with my original mass, sig figs, 3 sig figs. So 0.375 grams. Let's put that 5 in there. Okay, so 0.375 grams. Now the next question, how long will it take? The problem itself didn't tell me how long each half-life was, so I'm going to use this chart over here. Uranium-238, we see, has a half-life of quite a long time, 4.51 billion years. That's approximately the estimated length of the life of the Earth, okay? 4.51 billion years, the age of the Earth. So let's see how long that would take. I know that it was 4 half-lives, and each half-life was 4.51, I'm just going to say BY, billion years. So that's the calculation I need to do. So I'm going to go back to my calculator and do 4 times 4.51. And I get 18.04. I'm going to stick with 3 sig figs because of the 4.51. So 18.0 years. 18.0. Oh, sorry, billion years, not years. Billion years. That is definitely a difference. Okay, so we have a few more examples and we're going to speed through them without any narration. So here we go. So the examples that we've looked at so far, basically they work with nice, neat numbers, okay? It doesn't require any like algebra or tough math. It's just like baby half-life problems. So now we're going to look at some more messy number type half-life problems, okay? So if you don't have like an integer number of half-lives, let's say you wait 3.5 half-lives instead of 4. How do you work that? So we have this kind of crazy complicated looking formula. You don't really need to know where the formula came from, and you need to ask your teacher whether or not you need to memorize it, but we're just going to practice how it works, okay? So first off, we see this ln here. Remember, that's the natural log. If you don't really know yet from algebra what a natural log is, you don't need to know. Here's what you need to know. ln is right there on your calculator. You hit ln, and that's all you need to know, okay? It's called a natural log, and it's just a mathematical function that you'll learn about in math if you haven't already yet. So the natural log of the amount of substance that you have at the end, so the F stands for the final amount, equals the negative 0.693 over the half-life. So, you know, you'd put your 4.51 billion years or 1600 years, the length of your half-life right there, multiplied by the amount of time that you wait. You know, so maybe you're only waiting 10 days. Okay, you'd put that right there. and then you'd add the natural log of the initial amount. So again, AI is the initial amount, AF is the final amount, HL is the length of one half-life, and T is the amount of time that you're waiting. So it's not necessarily a whole amount of a half-life, you know. So let's do an example. It says determine the length of time. So we're going to solve for T, the length of time necessary to reduce 52 grams of uranium waste to 20 grams of uranium. The half-life is 4.5 billion years. So again, let's think about our formula. So it's the natural log of the final amount, which is 20, equals negative 0.693 over the half-life, which is going to be the 4.5 billion years, so we'll just put 4.5 right there. T is what we're solving for, plus the natural log of the original amount, which is going to be my 52 grams. So I'm going to plug my numbers in here, and then we'll do our algebra. So the natural log of my final amount, 20, equals negative 0.693 over 4.5, T for time, plus the natural log of my initial amount, which was 52. So I'm trying to solve for T, get it by itself. So my first step is going to be to subtract the natural log of 52. So minus the natural log of 52 from both sides. So that goes away. So I'm going to have the negative 0.693 over 4.5 times time equals whatever natural log of 20 minus natural log of 52 is. So I'm going to go to my calculator and do that subtraction. Natural log of 20 minus the natural log of 52. So natural log of 20, close parentheses, minus the natural log of 52. So negative 0.955. Negative 0.955. And then finally, to get T by itself, I want to divide by the 0.693 over 4.5. So I'm gonna figure out what that number is real quick. 0.693 over 4.5. 0.693 over 4.5 is 0.154. So I'm going to just substitute that in right here. 0.154 T, and make sure we keep the negative there. And this is negative 0.955. So to get T by itself, I need to divide by both sides by negative 0.154. So divide over here by negative 0.154. Sorry, I'm not having the neatest algebra here, but let's go ahead and go to our calculator and do this. So negative 0.955 divided by negative 0.154. This is going to give me my time. So my time is 6.2, whatever the unit for time was, which was billion years. So my answer is 6.2 billion years. I mentioned earlier that the estimated age of the Earth is 4.5 billion years. So we see that uranium waste is not something that goes away very quickly. In fact, it takes quite a lot of time. The last thing we'll talk about is what this half-life stuff can be useful for. Radioactive dating is a scientific process that can be used to figure out the age of fossils. So fossils can be dated, or we can determine how old they are by knowing the ratio of a parent element, which is radioactive, to a daughter element, okay? Two things need to be known: the length of the half-life of the particular isotope and the ratio in the substance for that parent and daughter element. Carbon-14 is the isotope that's most frequently used for this. It's used for things like wood or bones or old tissue, cloth, anything that used to be alive. The main idea is that all living things contain carbon, and they get their carbon by breathing in carbon dioxide. Okay, they also get some from what they eat from the environment, and they're constantly taking it in. A small portion of the carbon that we can have in our bodies is carbon-14, which is radioactive. Most of it's carbon-12. Small portion of it is carbon-14, radioactive. Now, after a living organism dies, it stops getting carbon from the atmosphere. So the carbon-14 that we usually are replenishing in our bodies and stays fairly constant begins to decay. So Here's a nice picture of like a mummy. Because we know that the half-life of carbon-14 is a very particular length of time, 5,730 years, we can measure the amount of carbon-14 and carbon-12. We figure out that ratio and calculate how long that organism has been dead. So we see a scientist here working on a mummy. I think this was from Egypt. And they can actually figure out approximately how long ago this person died. So that's what carbon-14 dating is. So that's just one application of the half-life of particular isotopes. So you could solve a half-life problem using carbon-14 and figure out how long ago something died. So thanks for watching.